Okay, so today we're going to start talking about exponential functions again. Again, we saw this is our most recent full unit, so this should be familiar, should come back pretty quickly. When we talk about exponential functions, we're on page 21 in your review packet, and we're looking at something that looks like this. So we can see we've got sort of this tapered end, which would be getting closer and closer and closer to what we call our asymptote. And then I am growing. Okay, we're growing. This is exponential growth because we're growing, but we could also have a function that looks like this. We would call this exponential decay, where we're shrinking as we move forward. Again, it would also have an asymptote. So two versions of an exponential graph here that we can look at. And of course, there are transformations, modifications we can make on either of these. These are the two biggies. Just like for our quadratics, we could have them opening up or down, or for linear functions, we could have a positive or negative slope. For our exponential functions, we could see exponential growth or exponential decay. In a table of values for an exponential function, what we should see is that for the same change in x every time, we will have a same change in y, but unlike our linear functions and our quadratic functions, we're not adding or subtracting, we're multiplying by something. So to get from a fourth to a half, we'd have to multiply by 2. To get from a half to 1, we'd multiply by 2. To get from 1 to 2, we multiply by 2. 2 to 4, we multiply by 2. So we're multiplying by the same number each time. This is, again, different than our linear and quadratic functions because in those we were adding or subtracting. Here we're multiplying. So we always multiply by the same number each time. I'm always multiplying by the same number. For exponential functions, we only have one function form that we're going to focus on. That would be this guy right here. A lot of times we do see something at the end, which we'll talk about in just a minute. But when we look at our function form, that a, particularly when we get to our problems in context, is what we call our initial value. Tells me where to start. And the b is our growth if we're growing, or decay if we're decaying factor. It tells me how we grow or how we decay. Now we did look at a modified version of this function where instead of just a value here, we had a percent change. And so we looked at 1 plus a percent or 1 minus a percent. But 1 plus a number or 1 minus a number, we could simplify to just be this. So this is really the only function form that we have when we looked at simplifying those percent changes. And we will see some percent change problems as we get a little bit farther in our unit. But for now, we're going to focus on if this is a single number, we don't have to do anything to combine or get it down to a single number. And then our problems in context, our applications of exponential functions look something like this. So we have a bear population in a national park. It's originally 6 bears and it doubles every year. Or maybe our bear population is originally 6,000 bears and that population decreases by 5% each year. Those would be both examples of exponential functions. One growth, the other decay. Okay. Today our focus is going to be on graphing exponential functions. So again, we're looking at exponential functions with the form y equals a times b to the x. And then I'm going to throw a plus c here at the end. Sometimes we have this number, some sort of constant term that we add or subtract at the end of our function. Remember, that's an important piece of information when I'm graphing. So I always start by graphing the asymptote of my function. That sort of boundary line, that force field line. And that comes from the number at the end of my function. If I don't see anything here, that means that it's 0. But if I see +2 or -7, that's where I'm going to put my asymptote. And then the next thing I want to graph is the initial value. Tells me where to start. So on the y-axis, I go up to or 4 below the asymptote. That tells me where I am in relation to the asymptote on the y-axis. And then the base for my exponent tells me how that distance from the asymptote changes. So I double the distance, or I cut the distance in thirds. Tells me how I'm changing that distance from the asymptote. We're going to start by graphing some functions. So we're going to be given the function and create the graph. And then later on, we'll swap that. So I'll give you the graph and we'll write the function based on the graph. So for number 1a, I want to start by identifying my asymptote. Remember, that's the number at the end. So my asymptote would be y equals 1. I want to go ahead and graph that. I need the asymptote in order to plot my initial point. There's my asymptote. And then my lead coefficient tells me how many units I am from the asymptote on the y-axis. So since this number is 4, positive 4, we're going to be 4 units above the asymptote. So on the y-axis, I start at the asymptote and I count up 1, 2, 3, 4. And I plot my point. Now the base for my exponent tells me how this distance changes. So I'm starting with a distance of 4. This number tells me as I move forward each time, we multiply the distance by 2. So right now we're at 4. Multiply that by 2 and our distance should now be 8. So 4, 5, 6, 7, 8. If I move forward again, I multiply this distance by 2. 8 times 2 would be 16. Now that's going to be pretty far off of our coordinate plane, what we have right here. So instead, I'm going to go backwards. Instead of moving forward, I'm going to move back. Remember, I always want at least 3 points from you when you're graphing a function. And if I'm going to move backwards, we reverse the directions. So instead of multiplying by 2 as I move forward, when I move backwards, we divide by 2. So my distance right now is 4. If I move backwards 1, I divide by 2, and now it's 2. If I move backwards again, I divide by 2, and now it's 1. Again, at least 3 points, and your exponentials graph always needs the asymptote. Once you've plotted your points, connect them, throw your arrows on the end. Questions for me on A? Okay. B, same idea. We're going to start with our asymptote. So I look at the end of my function and I see a plus 6. That means my asymptote is at y equals 6. So I'm going to go to 1, 2, 3, 4, 5, 6 on the y-axis and sketch in my asymptote. I like dashed lines for asymptotes, but if you want to do a solid line, that's fine too. The important thing is that it's on your graph. There's my asymptote. And now I look to that lead coefficient, that initial value, to tell me where to put my first point. This is -2. Since it's negative, that means I'm going to plot that point below the asymptote. So where I had a positive value, we were above. Since I have a negative value, we'll be below. So on the y-axis, I'm going to be 2 spots below the asymptote. And then again, the base for my exponent tells me how to change that distance. This says multiply it by 3. So my distance right now is 2. When I move forward, I multiply it by 3. 2 times 3 would be 6. So there's 2, 3, 4, 5, 6. If I move forward again, I'm going to multiply by 3 again. So 6 times 3 would be 18. There's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We're a little off the graph this time. That's okay. If I wanted to reverse directions and divide by 3 instead, I could. 2 divided by 3 isn't going to be a nice number, so I could just leave that as 2/3. I'd be 2/3 from the asymptote. So just ahead of that, oops, a little hard to see, just sort of ahead of that marker. Again, or grid line, I should say. Again, once you've got at least 3 points, connect them, throw your arrows on the end. Questions for me on B? Okay, go ahead and turn the page and we'll look at our next problem, C. 1C. I'm going to start with my asymptote again. Since I see a -5 at the end of my function, that means my asymptote's at -5. So 1, 2, 3, 4, 5. And again, make sure it goes all the way across your coordinate plane. And then we look to our lead coefficient to see where to put that first point. I have the number with the exponent, but I don't see anything in front of it. If I don't see anything there, what is it? 1. Yeah. I don't see a number there. It's 1. So that tells me I'll put my point 1 unit above the asymptote. And then the base for my exponent tells me how to change that distance. We have a distance of 1 right now. Since the base for our exponent is 4, that means as I move forward, multiply by 4. So 1 times 4 is 4. So 2, 3, 4. If I move forward again, multiply by 4. 4 times 4 is 16. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Again, just off my clock there. Once you've got 3 points, you can connect them. And don't forget to throw your arrows on the edge. Remember, your graph should never cross your asymptote. It acts sort of like a boundary or a force field. So I should never plot a point on the asymptote, and I should never draw my graph crossing the asymptote. I want you to try D now. Remember to start with your asymptote. Where's my asymptote for D? I don't see a number here at the end. So it would be at 0. Right along that x-axis. Where will my initial point go? 2 above. I look at that lead coefficient, that tells me 2 above. And then if I move forward, my base for my exponent is a half, so that tells me cut that distance in half. I'm at 2 right now, so cut in half, I'm at 1. Now we could keep moving forward. 1 cut in half would be a half, but that would get pretty difficult after a while. If you want to keep your points on the corners, remember we could always move backwards. So we're dividing by 2 moving forward, means we would multiply by 2 moving backwards. So this would be up at 4. Connect your points, throw your arrows on the end. Which of our functions and graphs from number 1 would represent exponential decay? D? Why is B not exponential decay? It's not exponential decay. Why is it not? Because what? Sorry. This one's tricky, right? Because it's upside down. Everything else is above. This one's below. I want you to notice that that distance as we move forward is still growing, still getting bigger. So when we talk about growth versus decay, we're talking about the distance from the asymptote. Is it getting smaller or larger? Here, we know that this one is growth because it looks like the one I told you above was growth. The distance from our asymptote gets bigger and bigger. This one is growth. Again, the distance from our asymptote keeps growing as we move forward. The other thing that we can look at is the base for our exponent. Anytime the base for our exponent is a number greater than 1, we have exponential growth. So this guy also, the base for our exponent was greater than 1, that's exponential growth. Over here for D, the base for our exponent is less than 1, that's decay. Okay. So if you've got a graph, you're looking at, am I getting farther from the asymptote as I move forward? here, I'm getting farther from the asymptote as I move forward. For decay, we're getting closer to the asymptote as we move forward. Or is the base for my exponent greater than 1 or less than 1? Now for number 3, we're gonna flip the script here. So we started with functions and created graphs. Now we're gonna start with graphs and write the functions that would describe those graphs. As I write my functions, I'm gonna go in the same order that I go in when I create the graphs. Okay, so I'm gonna start with the asymptote. I wanna start by identifying where's my asymptote. So for A, my asymptote is down here. There's -5, 6, 7, 8. We're at -8 down here. So I'm going to put a -8 at the end of my function, -8 at the end. When I'm graphing, the next thing I identify is where should I put my first point? On the y-axis, where does it go? So on the y-axis, my first point is here. That is 1, 2, 3, 4 spaces above the asymptote. So my lead coefficient here, my initial value, should be 4. And then the next thing we look at when we're graphing is what's the base for the exponent. That tells me how that distance from the asymptote changes. So I'm going to do the same thing here. I want to figure out what's the base for my exponent. So I have to look at the next, as I move forward, the next point, what's its distance from the asymptote. So 1, 2, 3, 4, 5, 6, 7, 8. My distance from the asymptote is 8. So I need to know, what did I multiply by? 4 times what to get 8? 4 times 2. So the base for my exponent would be 2. So I've got 4 times 2 to the x minus 8. Question for me on A? Okay, let's take a look at B. Again, we're going to start with our asymptote here. So we're up at 2, so a plus 2 at the end. And then on the y-axis, my first point is a 1 space above the asymptote. So I would want a 1 there. And then for my base for the exponent, as I move forward, I'm not on a corner. And it's a little difficult to tell exactly where that point is. It looks like maybe not quite a half, but is it a fourth? Is it a third? Is it a half? And I'm just like bad at estimating. So if it's not at a corner, it can be difficult to tell. Okay? So instead of moving forward to figure out that distance, I'm going to use our trick of moving backwards. Okay? So if I move backwards, I do have a nice point there. And this distance would be 1, 2, 3. So we're going to use this and say 3 times what would give us 1. Okay? 3 times what would give us 1? 1/3, yeah. So the base for our exponent is 1/3. I would like you now on the next page to try C and D. Write the equations for C and D on the next page. Where's my asymptote for C? 2. So I should have a plus 2 at the end of my function. Where's my first point? How far is it from the asymptote? Yeah, our first point is 2 below, so this would be -2. And then how am I changing that distance each time? So we have a distance of 2. Our next distance is 1. We're cutting it in half, right? Multiply by a half. Remember, this number always represents that change in distance as we move forward on the graph. And then how about D? Where's our asymptote? At 0. You actually don't have to write the plus 0 at the end if you don't want to. How about our first point? 1, we're always on the y-axis for that first point, 1 unit above our asymptote. The 1 you also don't have to write if you don't want to, as we saw in one of our earlier examples. And then how about our base for the exponent? As I move forward a spot, we go from a distance of 1 to a distance of 2. So it's 2, good. Which of the functions from number 3 represent exponential growth? D is growth. Any others? A, also growth. C and A. Okay, last thing for today. I would like you for number 5, everybody on their own is going to write an exponential function. I don't care what it is, as long as it's not one that we just did together, and the asymptote is not on the x-axis. Okay, so those are your 2 criteria. You are writing a function that's not one we've already done together today, and its asymptote is not on the x-axis. Then I want you to graph your function and answer your questions here. One reminder I want to give you, your y-intercept means what's your distance on the y-axis from the origin, not what's your distance from the asymptote, okay? So for y-intercept, remember, I'm counting what's the actual y value at that point, not the distance from the asymptote. I'm going to give you guys a couple minutes, get your function graphed and answer those questions, and then I'm going to come around and take a look at your work. While you're waiting on me to come around once you've finished, you can go ahead and work on your Delta math, but I will be around to check everybody's work today.